So this is a video about the equations for chapter 23. But before I talk specifically about the equations, I want to give you an analogy between gravitational fields and electric fields that will really help with figuring out whether positive work is done or negative work is done or things speed up or slow down. So if you consider the electric field case where you have charged plates that create a uniform electric field in the downward direction. And then the analogous situation is if you're close to the surface of the Earth, you have a uniform gravitational field also in the direction down. Now you know what's going on over here with the Earth and gravity. It's intuitive. You have a mass, it feels a force. The force of gravity is mg. And if you want to make g the vector, the gravitational field vector, that's fine. It's exactly the same over here. If you have a charge, Q, it feels a force, the electric force. And just like over here, you have M times G, M being the property that something has to have in order to feel a gravitational force. Over here, you have the electric force is QE. So the property you have to feel an electric force is charge times the field. So those two equations are pretty similar. Now, as far as energy goes, you know that if something is at a height h above the surface of the Earth, it will have a potential energy mgh, gravitational potential energy mgh, and if you let it go, it falls down, and as it falls, it loses potential energy and gains kinetic energy, and you have conservation of energy. Exactly the same things going on over here. If you have a charge up here, now your textbook uses U for electric potential energy, but I like to stick with PE because it's obvious, potential energy is equal to, instead of M, you have charge. Instead of gravitational field, you have electric field. And instead of height, we just call it a distance, delta D. Because it doesn't have to be vertical, whereas over here in gravitational field, this is always vertical. You could turn this picture sideways, and so delta D is the distance. And similarly to the mass, if this charge falls down, it picks up kinetic energy, loses potential energy, and energy is conserved. Okay, now something else that is completely different for electric fields compared to gravitational is that there are negative charges. Now, as far as negative mass goes, that's a whole nother lecture. But over here, there are negative charges that do everything backwards. So a negative charge would actually fall up. And because it's falling, just like a falling mass, it will lose potential energy and gain kinetic energy. So this thing will accelerate up. And the force on it, the electric force, is up because of this negative charge. So it'd be negative QE. You do actually put the negative value in there. But everything else is the same. It has kinetic energy, potential energy, energy is conserved. It just goes the opposite direction. As far as work goes, we know intuitively over here with the mass that if you lift something, so if you lift it, you lift M, you do positive work. The field does negative work because the field is in the opposite direction to the motion of the mass. Okay, so you have to keep this straight. So you lift M, you do positive work, the field does negative work. Exactly the same over here. If you lift the charge, so this is identical. So you lift, you do plus work, and the field, the electric field, does negative work. And that is why there's that negative sign in the very first equation here, where it says that work is equal to the negative change in potential energy. That is always true, because the work they're talking about is the work by the field, not by you. And that's why there's a negative. Okay, so the field's always trying to pull it down, You have to work against that, and that's how potential energy goes up, you working against the field. Okay, so that's work by field. So that's the first. Now I have done a video of examples of charges moving in electric fields and conservation of energy. Now, another property that we have with electric fields that we do have with gravitational fields over here, but you don't get to that unless you do third year physics. And that is this property called voltage. Now, it is definitely related to electric fields, but it has nothing to do with this charge that you're moving around. It's just a handy quantity to define so that we can talk about changes in energy in electric fields. And the way it goes is voltages are defined to be lines, just completely imaginary, abstract lines in space that we define a voltage for. So let's go down here. So what's going on with voltages? We have these plates. And in order to charge plates, metal plates, you have to hook it up to a battery. And so that's how you get these electric fields. You need the battery. And so if this is the battery, and the voltage here is say 12 volts, a 12 volt battery, that means the potential up here is 12 volts, and the potential down here is 0 volts. Now that's just by definition. We could have the potential at the top plate 24 and at the bottom 12. It's just the difference that counts. It has to be 12. And so this line along this plate is the 12 volt line, and this is the 0 volt line. Well, everywhere else is halfway would be the 6 volt line. And halfway between there would be the 9 volt line, and so on. This would be the 3 volt line. And these lines, the definition of these lines are places in an electric field. So it has to be an electric field, or you can't have voltage lines. And it means that when you move along these lines, no work is done. So it is similar to a gravitational field. If you take a charge and move it sideways, it doesn't take any energy, it doesn't take any work, because you're moving perpendicular to the force, and so there's no work done. And so these lines are also sometimes called equipotential lines. And they're just lines of constant voltage. And they just kind of make it handy. So if we want to know, say something goes from the 9 volt line and then moves down to the 3 volt line, what's its change in potential energy? And so the formula, the change in potential energy is equal to Q times the change in voltage. And so notice how if you move down, the potential energy goes down and the voltage also goes down. So these are in the same direction. And so say we move the 1 coulomb charge from the 9 volt down to the 3. So you go final minus initial. So this would be negative 6 joules. The object would lose 6 joules of potential energy as it moved down those lines. Now it will fall. A positive charge falls from high voltage to low voltage. Similarly, it falls and its potential energy decreases. So that's a handy, this is just a handy thing to do to talk about changes in potential energy. Okay, so that takes care of the first equation. Now, another equation that has to do with potential energy that's on your formula sheet looks like this. KQ1, Q2 over R12. Notice how it's not R squared, it's just R12. I've done a video of this. This has to do with the amount of potential energy stored up in the configuration of charges. So for example, if you want two charges, Q1 and Q2, to be separated by some distance R12, somebody had to push on Q2 to get it there. So if these charges started out with no energy whatsoever out here at infinity, this place is infinity. To bring the first charge from infinity over, say this is Q1, to bring it over here to this location, it doesn't take any energy at all because there's no field, there's nothing to push against. You can just move it here. So single charges do not have any energy associated with them. But now to pick up Q2 and bring it to here, because now there's this electric field everywhere around Q1, you have to push. And the amount you have to push to bring it over here, that is this. That's how much energy you've put into the system. And this is true if you don't have to have just 2 charges, you could have a whole bunch of charges. So if I wanted to now take Q3 and bring it over here, not only would I have to work to push against the field from Q2, but I'd also have to work to push against the field from Q1. And so it takes a lot of energy to get Q3 over here. And in general, the total is the sum of all the possible pairs, Qi, Qj over Rij. And like I say, I've done a video, it's called Potential Energy of a Collection of Charges, and you can look at that video. Okay, the next thing on the formula sheet has to do with the voltage due to a point charge. And so now this is not the parallel plates, this is a point charge. So what this means is, now there is an analogy here. When you have a charge Q, it creates this electric field everywhere around it. Now this is not a uniform electric field. These electric field lines are getting further apart. This field is getting weaker and weaker. This is KQ over R squared, R hat. But associated with that electric field, there's always voltage lines associated with electric fields. The voltage lines are now circles. And so these voltage lines, the voltage decreases in the direction of the field. So if this is a 100-volt line, this might be the 50-volt line, the 25-volt line. Now the voltage lines are not equally spaced because they're proportional to 1 over R up here. So they do get further and further apart. This might be the 5-volt, and so at infinity, you finally get to the 0-volt line. Okay, and I think I've probably done a video of calculating the voltage due to point charges. And of course, one of the classic questions, similar to the one that lots of you had on the midterm, is if you have 2 charges of unequal charge, say 10 microcoulombs and -2, you know how to figure out where the electric field is 0, but now there's also a location where the voltage is 0 and is not the same place as where the electric field is 0. And there's actually 2 answers. And I've done a video of this. It could be over here, but it could be here too, because voltages aren't vectors, they're scalars. And all you have to do is add the 2 voltages to get 0. So you don't have to worry about direction. So there is a video of this, video where V equals 0. Okay, now the next thing is integration. So you know how you did the rod, the ring, the disc integration? Well, there's the rod, the ring, the disc for voltage as well. But it's way easier because it's a scalar. You don't have to worry about vectors or components, and there's no R squared, it's just R. But you do exactly the same thing, and I've made a video of this. You break up the rod or the ring or the disc into little pieces. You integrate around the pieces. You don't have to worry about components. And you come up with the formula for the rod, the ring, the disc. Okay. I don't think there are a lot of those on your Master in Physics assignment, so we didn't do too much of those this year. Okay. Another thing that's related to calculus is the relationship between electric field and voltage. It's just like velocity and acceleration. So you know how the acceleration is equal to the derivative of velocity? Well, the electric field is equal to the derivative of voltage, except for it's not just one derivative, it's the gradient of the voltage, which from your math course, you should know what the gradient means. Remember, the gradient means it's a vector operator, d by dx of v, and then the I hat minus dv dy, j hat minus dv z k hat. Okay, so the derivative of voltage gives you electric field, just like the derivative of velocity gives you acceleration. And you can turn this around. The change in velocity is the integral of dv, which is the integral of a dt from 0 to t, from v initial to v final. And so just this A equals dv dt is called a differential equation because it's a derivative. This is called the integral equation. Similarly over here, this is a differential equation because it's got the derivative. But then you can do the integral equation, delta v, which is the integral, now there's a negative here, of E dot ds. And I've done a video of how to do both this derivative and this integral. Okay, so that's pretty well it for the equations for chapter 23.